even of group 16 ended with 6 electrons in the outermost shell. In other words, NS2, then NP4. In the case of a halogen, group 17, the outer electronic configuration is NS2, 2p5, all true. So 6 and 7 electrons, respectively, for group 16 and 17. So we went on to discuss the color. It has gone.
Yes, yes. Thank you.
And electronegativity. So that is how far we left during the last class. Now, before I speak about oxidation state, let me briefly discuss bond dissociation energy. The bond dissociation energy follows the order chlorine greater than bromine, bromine is greater than fluorine, and iodine. So now oxidation state. The oxidation states displayed by these elements. For instance, you have fluorine -1, -1. So don't forget that these elements attract one electron to attain the next noble gas. plus 5, plus 6, and plus 7. While bromine exists as plus 1, plus 4, plus 5, and plus 6. Iodine exists as minus 1, plus 7. So these elements, as you can see, they have of ns2, that is 2 electrons in the s orbitals, and 5 electrons outermost electronic shell. Each halogen atom in its ground state can one electron from an element which is less electronegative than it. For instance, in the group 1, you are familiar with the trend negativity increases across the group. So the least electronegative elements are the group 1 metals. So while the highest electronegative elements are the halogens. So each of the halogens can accept 1 electron from any of the group 1 metals to form the halide. For instance, the fluorine, arsenium, or potassium, um, or lithium, it will form MF, MF, that is metal fluoride. So the electronic configuration of the fluorine fluoride ion here will be 2s2 and 2p5. Likewise, if it happens to chlorine, the chloride ion will be 3s2 3p5. So, or by sharing electrons uh, each of them donate 1 electron for sharing. Each of the halogen donate 1 electron for sharing. So oxidizing power. due to fluctuations.
The network is
Sorry. So shortly before the disruption, we were talking about the oxidation state. So now, when it when it combines with an element having greater electronegativity, it exhibits +1 oxidation state. Since fluorine is the most electronegative element, it always shows -1 oxidation state. It shows -1 oxidation state. Now, if you look at group 17, fluorine is the most electronegative. So, but an electronegativity increases down the group. It increases down the group. Since it's the most electronegative element, it always shows -1 oxidation state only. It does not exhibit any positive oxidation state. Chlorine, bromine, and iodine have vacant d orbitals in their valence shell and therefore can have excited states. So, chlorine, bromine, and iodine can promote their s and p electrons to the vacant d orbitals, which makes them possible to exist in higher oxidation state. So you can see that chlorine, for instance, is closer to the d orbitals. So the electron from the 3s orbitals and the 3p orbitals can be promoted into the d orbitals, and that allows it to form higher oxidation states like a +3 +4, +5, and even up to +7. Likewise, bromine and iodine. So since fluorine atom has no d orbitals in its valence shell, it cannot have any excited state and consequently cannot exhibit some of three d10 and 4p5. The energy required to promote an electron from 4s orbitals of the atom in the second excited to 4d is markedly higher than the required for by chlorine. Thus, bromine does not exhibit a +7 oxidation state. You are to note that all the halogen except fluorine are less electronegative than oxygen. All the halogens except fluorine are less electronegative than oxygen. So they show positive oxidation state in their oxygen compound. When chlorine, bromine, iodine combine with oxygen, they show positive oxidation state in all their Cl in ClO2, Cl in okay, Cl in AClO, Cl in AClO2, ClO3. So you have +1 here, then +2, +3 in AClO3, and +7. These are the oxidation states shown by chlorine when it combines with oxygen. So, oxidizing power. They are strong to attain the next noble gas configuration. If you see fluorine, the next noble gas configuration is neon. So on accepting an electron, the electronic configuration of fluorine, chlorine. Chlorine is 17. When it accepts an electron, so it becomes a what? A chloride ion, which is a 18 electron, which is the argon configuration. However, the oxidizing power decreases in this order: fluorine greater than chlorine, chlorine greater than bromine, and bromine greater than iodine. What that means to say is that if you have a potassium uh, potassium chloride, for instance, and you have to pass in fluorine gas into potassium fluoride. Then, because fluorine has more oxidizing power than chlorine, chlorine displaces the fluorine displaces the the chloride ion from potassium chloride. Likewise, here, chlorine gas, when it is passed into potassium bromide, because chlorine has more oxidizing power than bromine, chlorine will displace bromine from a solution. And that accounts, this is why you have Cl2 reacting with a 2 kBr to give you 2 KCl plus Br2. So in this order, bromine will displace iodine from solution of hydrogen iodide or even sodium iodide, as the case may be. So reactivity with hydrogen stroke formation of halogen acids. They react with hydrogen under different conditions to form different halo acids or halogen acids, as the case may be. So the affinity for hydrogen decreases from fluorine to iodine. From fluorine to iodine. Fluorine reacts with hydrogen explosively, even in the dark. Fluorine will react with hydrogen in an explosive manner, even when it is dark, while bromine react on heating above 500 degrees Celsius. Iodine will react with hydrogen only on red hot and using platinum as a catalyst. So oxidizing power, however, decreases in the order of fluorine greater than chlorine, greater than bromine, and greater than iodine. In other words, oxidizing power of this halogen decreases as you descend the group. As you descend the group. Going down the group, then fluorine is more powerful than chlorine. Chlorine is more powerful than bromine, and iodine is the least. Some general characteristics of halogen acid. The acidic strength, e.g., proton releasing power. What is an acid? By definition, an acid is a proton donor. So an acid is any substance that has the capacity to release proton. Okay? While a base, what happens to a base? A base will accept a proton. So the acidic strength of this HX acid follow the trend as explained. HF is less than ACl, ACl is less than HBr, and HBr is less than HI in methanol solvent. That is, hydrogen fluoride is less than hydrogen chloride. Hydrogen chloride is less than hydrogen bromide, and hydrogen bromide is less than hydrogen iodide. So in aqueous solution, acidic strength increases with increasing heat of with increasing heat of stability. So stability, the stability is H hydrogen fluoride greater than hydrogen chloride, and hydrogen chloride greater than hydrogen bromide. Hydrogen bromide is due to decrease in the strength of hydrogen halogen bond. Hydrogen halogen bond, HX bond, hydrogen. X represent halogen. Hydrogen halogen bond from hydrogen to fluoride, hydrogen fluoride bond to hydrogen iodide bond, and hence decrease in the bond, there is decrease in bond dissociation energy. Now, boiling point. The boiling point of hydrogen chloride is less than boiling point of hydrogen bromide. And the boiling point of hydrogen bromide, but all said, all the three, they are less than hydrogen fluoride. One of hydrogen fluoride should be more than the remaining three, but the reverse is now the. Why is it that hydrogen fluoride has the highest? Some general characteristics of HX, for instance, ionic character. Ionic character. Remember that we said are generally what? They are generally basic. The HX or hydrogen halides ionic character decreases as you descend the group, because HF, the F is a gas, chlorine is equally a gas, then Br is a liquid, then iodine is a solid. Between the halogens, HF is the most ionic, and hydrogen, the dipole moment, the same explanation goes. Now, if you look at oxidizing power, then acidic character, then the reverse is the reducing power. So hydrogen fluoride is less than hydrogen chloride, and hydrogen chloride is less than hydrogen bromide, while hydrogen bromide is less than hydrogen iodide. Of halogen with metals. Any of the halogens, M here represent any of the metals. So now, when a metal is bound in the presence of halogen, then you have a reaction of halogen with metals. Burning of metals in the presence of halogen will result into metal halides. There is formation of metal halide. For instance, metals react with fluorine gas to give you metal fluoride. Sodium, for instance, will react with chlorine to give you sodium chloride. So ionic character of this metal chloride decreases in the order of fluoride greater than chloride, chloride greater than bromide, and bromide greater than iodide. So the halides in higher oxidation state is more covalent than those with a lower oxidation state. And that shows that the halides in the minus one oxidation state, they are purely electrovalent. They are electrovalent. Then halides in the plus one oxidation state, all down, are what? It's more covalent than that of the halides of group 1. Interhalogen compounds. Reactivities of halogen towards other halogens. That is when halogen can combine with other halogens to form binary compounds of different halogens and different formulas. For instance, binary compounds of different halogens with this formula XXN. X represents halogen, and Xn is equally halogen. So, but fluorine cannot combine with itself. It is the most electronegative. It can't combine with itself, but can combine with all other elements, can react with all other elements down the group. For instance, you have a compound of chlorine and fluorine. You have compound of fluorine and bromine. You have compounds of chlorine and bromine, and you have compound of iodine and chlorine. So any halogen above the other halogen will definitely form compound with the one below it. So when n is equal to 1, then you have a F. That is a what? CLF. That is fluoride, I mean, fluorine of like fluorine BRF. You have a BRCL as well. And when N, that is when F3. Have BRF3, IF3. N is equal to 1. They are all linear in shape. They are all linear in shape. When N is equal to 3, structure. And where you have a CL5, BR5, IF5. IF5. The shape is a halogen oxygen compound. Remember that we said oxygen, but oxygen, they are all uh, uh, electronegative than not react directly with oxygen. They are prepared by indirect methods. Examples is oxygen fluoride, oxygen fluoride, which is a peroxide of oxygen ClO, Cl2, then ClO2, 2O, I2O4, and so on. Formation of oxyacid. All halogens form oxyacid except fluorine due to its high electro, except fluorine due to its high electronegativity. What do you mean by oxyacid? Remember, you have hydrogen chloride. Then you can have these, there are four types of the halogen acid that the halogen is plus one. Then where the halogen is plus three, the oxidation number of halogen is plus one, plus three, then plus five, then we have up to even plus seven. Okay, so and these are dyspromine and iodine. However, the acidic strength in oxidation number, acidic strength is that of chlorine greater than bromine and greater increases with increase in oxidation number. Hence, the ACLO is less than ACLO2. ACLO2 is less than ACLO3. And ACLO3 is less than HClO4 is the most See. It's not moving? Okay. Is that it? Is that the point? Okay. So the acidic character increases with increase in oxidation number. Hence, we have this order. Now, by and large, let's quickly go through the carcogens and the halogens in general, because with this, we have successfully completed group 16 and group 17. Our next lecture now, our next two lectures will be on the transition metals or the transition elements. So the carcogens, electronic configuration. I'm just revising. So electronic configuration, the outer electronic configuration, 6 electrons, 2 electrons in the s orbitals, and 4 electrons in the p orbitals. The halogens, 2 electrons in the s orbitals, 5 electrons in the p orbitals. Oxidation state for oxygens, then is from minus for group 16, -2, +2, +4, and +4 oxidation states. Then oxidation states for halogens, we have -1 in all, then except fluorine, +1, +3, +4, +5, +7 oxidation state exists for chlorine. So all other halide exist in a higher oxidation state. So the ionization melting points, metallic characters, electron affinity, then polymorphism in group 16. Polymorphism, for instance, oxygen exists as ozone, sulfur exists as a monoclinic and a rhombic, even plastic sulfur. To form multiple chains. And group 16 and group 16. Water is an example of hydride of oxygen. Hydride of sulfur is a hydrogen sulfide. We have hydrogen selenite. The acidic character was explained there. Are formed when these groups combine with oxygen. When you have a group 1 with oxygen, you have a metallic oxide, which is because if it reacts with the water, it forms hydroxide. Acidic SO3 is equally acidic because acids. There are monoxides of the formula MO. For instance, we form monoxide. So you have dioxides. For instance, we have SO2. We have a tetroxide, which is a SO4. The formation of halides is more electronegative than oxygen, like earlier said. So, having said that, we have acidic oxide, basic oxide, and phosphoric oxide, and neutral. So the neutral, for instance, CO, N2O, NO, then O2, NO2, and so on. The neutral oxides, okay, oxides are the oxides of metals. For instance, sodium oxide, potassium oxide, basic oxide. The amphoteric oxide, for instance, you have is amphoteric because it reacts with water to give you the hydrogen, maybe silicate, tellurates, and so on. Okay. Sulfur, you have yellow sulfur, monoclinic, so and 96 degrees Celsius. 96 degrees Celsius. H2 hydrogen. Sulfuric acid is prepared using quantum pentoxide. Now we go to halogen. As a form of revision now. Okay. We said earlier that all the halogens are diatomic in nature. So that's the electronic configuration. Electronic configuration NS2 and NP5. 7 electrons in the outermost shell. And electrons to go off from 7 because of strong attractive forces. So halogen to accept an electron from a lesser electronegative element to be to attain the next noble gas configuration. And that is why you have fluoride ion having to attain neon configuration chloride ion with fluoride ion attaining neon configuration, and fluoride ion attaining argon configuration. Okay, so while bromide ion attains uh, krypton, krypton configuration, and so on. The color, they are all colored, like we said. So they absorb light in the visible region. Outer electrons from fluorine to iodine due to increase in size of atom. So, however, there is progressive deepening. Fluorine will absorb violet light and appear as yellowish green. There is ionization energy follow the same trend. As earlier discussed, electronegativity the same. Then oxidation state, as earlier discussed, that one oxidation state only. So although minus one oxidation state in all the compounds of the group. For instance, you have chlorine existing as minus one, bromine existing as minus one as well, and iodine can exist as minus one. However, down the group, then chlorine, from chlorine to iodine, they exist in higher oxidation states from +1, +3, +4, even up to +7 for chlorine. So +1, +3, +4, up to +6 for bromine, and iodine +1, +3, +4 is rarely known, +5, +6 is rarely known, and we have a +7 as well. So oxidizing power decreases in the order of fluorine to iodine, and that means all halogens can displace iodide ion. Bromine will displace iodine, and chlorine will displace bromine. Fluorine will displace chlorine in hydrogen chloride. So while chlorine will displace bromine in hydrogen bromide. Bromine will displace iodine in hydrogen bromide. When I say hydrogen bromide, HBr, is it that? Okay. 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 Thank you. Thank you. Thank you. Thank you. So, okay. Okay. So, some general characteristics of hydrogen halides. They are well spelled here, so you have seen them. Some general characteristics: ionic character, dipole moment, reducing power, reaction of halogen with metals, as it is stated here. So, interhalogen compounds, that is, halogen compound with itself with other halogens, chlorine and fluorine, bromine and fluorine, bromine and chlorine. These are these with the formula XSN. They, they are covalent and they are more reactive than halogen, except fluorine. So, and even more polar. So, and a little higher melting point than even halogen. Binary formation of binary oxygen uh, that is oxygen and other halogen oxygen fluoride, oxygen chloride. This may be hydrogen and halide. So, and you have it minus -1, +3, +4, +5, and +6, as the case may be. Increases with increase in oxidation number. So with that, we'll start transition metals or transition elements tomorrow. And that will take us another 2 hours. Thank you. To see you some other day. See you tomorrow.
Oh,
Ẹ ṣé. God bless you. What's the name?
Mary, sir.
Okay, Mary.